All right, we are now live. So, to the University of Central Arkansas's Society of Physics students 2015-2016 seminar series. We're lucky today to have with us Dr. Robert Hovden. He is a postdoctoral researcher at Cornell University in the Applied and Engineering Physics Department. Dr. Hovden is a postdoctoral researcher. His work focuses on understanding how the structure of materials at the atomic and nanoscale determines the mechanical, electrical, or chemical properties of the material. Primary focus has been in the development of advanced scanning transmission electron microscopy, methods for improving the structural understanding of 2D and 3D materials. This publication spans a wide class of systems involving 2D materials, including graphene, boron. You'd have to explain that.
Boron nitride.
Boron
nitride. Yeah.
That's damn it, Jim. I'm a physicist, not a chemist. Silicon oxide. I think I got that one. Hydrogen fuel cells, block copolymer networks, mollusk shells, which that sounds pretty interesting. Batteries and semiconductor devices. He earned his PhD in applied physics at Cornell University and a bachelor's degree in physics from the Georgia Institute of Technology. So again, I want to thank Dr. Hovden and our seminar series sponsors, the University of Central Arkansas Department of Physics and the University of Central Arkansas Foundation. So thank you, Robert, and take it away. You now have the floor.
Yeah, again, thank you for the opportunity to communicate to young students that are interested in physics, but really all areas of science. Hosting these seminars is very forward-thinking in a technological way. Before I begin the presentation, I wanted to show you the instrument behind me. So I'm a postdoctoral scientist at Cornell University. More specifically, I work under Professor Kirkudis, and her lab in the School of Applied Physics is building a new microscope for the university that will specialize in looking at atoms at low temperatures and looking at liquid-solid interfaces. So if you can cool samples down, you can look at phase transformations, and you can also look at things that would normally be liquid at room temperature but become solid. So the instrument behind me is a big tool. It's hopefully going to be up and running very soon. It's a complex machine. At the top of the machine, electrons are ripped from a nanoscale tip. They're accelerated to relativistic speeds. These electrons come flying down the column as quantum mechanical waves, and they crash into the samples that we put in front of them. And when they hit these samples, they scatter, and they scatter in particular ways that we can use to understand the material. And they interact with the energy states inside that material and give off unique spectroscopic signals. So if we can take all that information and collect it in an understandable way, we can learn something new about the materials we're interested in. So this is the lab that I would this is a representative lab that I would normally spend many hours and nights in. And with that gives you a little bit of context. I'll jump into the slides. All right, so I need to figure out the screen share system. Okay, do you guys see the slides?
Yes, sir.
Great. So with that, I'll begin. The title of my talk is Seeing Atoms with High Energy Electrons. Of course, I don't intend to say that we can actually see matter with our eyes. It's clearly too small, the atomic structure at least. However, we can see the these nanoscale worlds, through the use of high energy electrons. The electron beams can be precisely controlled with the use of an electron microscope. And when I say precise, I mean we can actually position a tightly focused electron beam between two atoms. And if we move that beam around, we can form images of atoms. So the picture on the left is a picture of a nanoparticle. The nanoparticle's, I don't know, roughly 20 nanometers in diameter. In the center, you'll also see spots in the nanoparticle. These spots are the atoms that make up the particle. You can see that these atoms are very well organized in a repeating pattern, which is what defines a crystal. So I'd actually call this nanoparticle a nanocrystal. Electron microscopes also allow us to explore nanoscale materials in 3 dimensions. On the right is a reconstruction of platinum copper nanoparticles. You probably noticed that there's a pore structure inside of them, which we are interested in characterizing in 3 dimensions. We wanted to know what the surface morphology looked like and what impact that would have on the catalytic activity. So we did this 3-dimensional imaging, which I'll talk about later, called electron tomography. So what this talk is really is an introduction to the physics of high-resolution electron microscopy and how we can use that to solve materials problems. So let's go down to the nanoscale. You're probably familiar with the term nanoscience, and you know that it pertains to things that are small, really small. But I want to make sure everyone here that's listening is comfortable with the scales that we're talking about. So let me take you down to the nanometer scale using parts on your person. Let's consider the phone as an extension of the human body. We can debate what defines a cyborg, but my phone is always attached to me. So your phone, it's 11 millimeters tall, 8 millimeters in its thinnest dimension. The manufacturer might tell you this is small, but to me, as a nanoscience scientist, your phone is huge. But if you have a phone, you've probably noticed that the pixels on the screen are tiny, or maybe you haven't noticed them, which is the point. Modern phones have pixels that are around 80 microns. This is what they claim with the retina display, which is right around what our eyes can discern, and it's also right around what a human hair is. So at this scale, at the 100 micron scale, we're really in the limits of what our eyes can resolve. If you go smaller than that, things become invisible to the naked eye. So the blood cells in your body, the red blood cells, are invisible to your eye. They sit at around 10 microns-ish. So we need an optical microscope to see red blood cells, things on the micron scale. But to a nanoscientist, 10 microns is still very big. We need to go 1,000 times smaller than that to get to the heart of the nanoscale, which is around 10 nanometers. The floor of that nanometer scale would be the width of DNA, which is around a nanometer or 2. So again, the nanoscale is 1,000 times smaller than the micron, and it's also what is on the scale of the devices inside your phone. So the computer chips and the memory are all at this nanometer scale, and there are billions of them that work together to make that phone perform the way it does. So why are we interested in this scale? What's different about the nanoscale? There's a lot to say about that. I can help build your intuition with a couple examples. One reason is that there's a dramatic change in the surface to volume ratios. So many chemical processes and interfaces, the interfaces in these, what I want to say is that the surfaces in these chemical reactions are usually the catalytic sites. And if we want to facilitate a reaction using these catalysts, we need to increase surface area. If you look at a 1 centimeter cube, it might have a total, so it'll have a total surface area of 6 square centimeters. But if we break that cube into 1 millimeter cubes, the surface area jumps to 60. If we take it all the way to nanometer cubes, we get 60 million nanometer surface area of these nanometer cubes. Another thing to say is when we're at these 10 nanometer, if we have a 10 nanometer particle, which is a reasonable size for a nanoparticle that's being engineered as a catalyst, 20% of the atoms in that 10 nanometer particle have atoms that are on the surface. So 20% of the particle's atomic weight is going to contribute to catalytic activity. In hydrogen fuel cell vehicles, platinum is a very valuable catalyst, but platinum is also an expensive catalyst, so you want to use as little platinum as possible. So you want to maximize this surface to volume ratio. Another example is quantum dots. When we go to scales similar to the quantum mechanical wavelengths in materials, we can tune the nanoscale dimensions of a material to alter the quantum mechanics of the system and its optical and electronic characteristics. So here I'm showing one visually striking example of quantum dots. These semiconductor nanocrystals, they're cadmium selenide core, zinc sulfur outer shell particles, where the band gap in these things are tuned by changing the core size. So as the particles go from 6 nanometers down to 2 nanometers, they fluoresce different frequencies of light when you excite them with an ultraviolet light source, and you get this gorgeous spectrum of colors. So this is a popular example of nanotechnology to share because of its striking appearance. But there's also real applications for LED technology and solar cells, among other things. Maybe the most dramatic impact nanotechnology's had on our lives pertains to the computer. So Moore's law states that the number of transistors on a chip doubles every 2 years. And this rule has held up surprisingly well. Since the 70s, we've been able to consistently jam more things into a computer chip. But doing so has required modern transistors and memory to go from micro to nanoscale. Here is a plot, on the left is a plot of the transistor count that we've been able to fit versus time, the number of transistors we've been able to fit into a wafer over time. And on the right, I'm actually showing the gate oxide in the transistors. It's showing the thickness of this gate oxide. It tops out at 2003, but the point here is that we've scaled things down from 12 nanometers in this particular example, 12 nanometers down to 1.5 nanometers. We're hitting dimensions at the atomistic level. I mean, at 1.5 nanometers, there's only a few atoms in this gate oxide, and shrinking down these components and the devices of our computers isn't just about putting more in. We also get performance improvements. Things go faster and they're more efficient. So I think anytime you're using a computer, talking about a computer, you're really talking about nanotechnology. So we're all leveraging it every day. And while we can engineer things on the nanoscale in ways never before possible, nanotechnology is still an ancient thing. Nature's been using nanotechnology for a long time. So one example I found was the magnetotactic bacteria. Within it has organelles containing magnetic nanocrystals that it uses for navigation. And I also found an example of the surface of a lotus leaf that has nanoscale structures to make hydrophobic surfaces for kind of a self-cleaning process. So you can find lots of examples in nature. One that I've worked on was mollusk shells, and if you open up some mollusk shells, you'll find an interior form of the shell called nacre that has great mechanical properties. If you look on the image I'm showing now, on the left side is the outer part of the shell, and the right side is the inner part of the shell. And the nacreous region is this lighter region. And so we were interested in knowing the nanoscale mechanisms of formation for this nacreous layer. So the outer shell is made of a different structure. They're all calcium carbonate, but they have different structures on the atomic scale and on the nanoscale. We wanted to see what happens at the transition from this outer shell to the inner nacre shell. And when we looked at it, we found a complex transition between the two layers, and it's all happening at the nanoscale. So the image A on the left is at the very bottom is the termination of the outer layer, this prism shell. But as it goes to the nacreous layer, then it puts down some organic goop, and then it starts depositing these little nanocrystals. And these nanocrystals assemble in a sort of diverging fibrous way, and they pack with higher and higher density. And then eventually, they form continuous nacre tablets. These are the layered things you're seeing at the top of the picture. So this whole process is entirely governed by nanoscale processes. So the point here is just to say that things exist at all scale, both natural and man-made. We have this continuum of scale, and what I'm interested in is the nano world down to the atomic, both in the natural and man-made world. There is a demarcation point that I think separates the micro world from the nano world, for me at least as a characterization person, and that's this what's happening here at this visible light spectrum. So the visible light spectrum, this is where the wavelengths of light, these are the wavelengths of light that we see, and they have a size. They're several hundred nanometers, and anything below that is difficult or impossible to see with visible light. So at that point we're dealing with things smaller than light. So light microscopes have been really good at seeing small things for a while. The resolving power of the microscope has hit the wavelength of light since the turn of the last century. So if you wanted to see things that were micron scale, you could use a microscope with 500 nanometer resolution and do just fine. But the question is, how can we resolve the nanoscale? How do we go further than what light microscopes can offer? And to answer that question, we need to understand what limits resolution. So if we have an optical lens, it'll have a resolution associated with it. Here I'm using D0 to denote the resolution. So what resolution is telling us is our ability to resolve two distinct objects. So at the top right, I'm showing two objects. Let's say they're atoms, and they're spaced a couple angstroms apart. I guess I haven't really defined what an angstrom is, but an angstrom is a tenth of a nanometer. So 10 angstroms in a nanometer. Think atomic scale whenever I say angstrom. Think a tenth of a nanometer, and think on the scale of the spacing of atoms. So if we had two atoms, we need a good enough microscope to resolve them. And as we bring them closer, eventually we'll hit the resolution of limit of our microscope. This is often considered to be the Rayleigh criterion, which I'm showing. Can you see the cursor moving, by the way? Is that
moving a little bit? Yeah, I can see it.
Okay. Yeah, so the Rayleigh criterion is what defines the resolution limit of our microscope. And everything after that, these two objects that we're trying to distinguish become single blobs. We can't really tell if there's one or two blobs inside them. So there's a formula to describe the resolution of a microscope. And the thing I want to point out is its relationship to wavelength. That the wavelength of light is directly related to the resolution. If you can make this wavelength smaller than your resolution, you can resolve smaller things. So the wavelength of visible light at 500 nanometers, you're kind of stuck around that ballpark in terms of what you can see with the best optical lenses. If we want to really go into the atomic or nano world, we got to reduce this wavelength. One thing that has a really tiny wavelength is an electron. So a 100 keV electron, it's a fast relativistic electron, has 0.0037 nanometers. So it's plenty good to resolve an angstrom or two atoms or the nanometer, certainly the nanometer world. But the idea that an electron or that matter is a wave is something worth reminding ourselves. It was de Broglie in the 20s that proposed that electrons had an inherent vibration associated with them. That matter was somehow a wave related to its energy and momentum. So shortly thereafter, people started sending electrons into crystals to see if they scattered in a way that was like waves. Davidson and Germer did experiments in 1927, Thomson as well, and found that these things did scatter. They scattered in predictable patterns that were consistent with waves hitting a crystal. Kikuchi shortly thereafter did nicer experiments. I would say qualitatively, at least, that these images looked really beautiful. So I'm showing one of his images. This showing that electrons are waves would earn them the Nobel Prize later. For us today, we just want to leverage the small wavelengths to resolve structures and materials. So you can do that. We don't need to go through the details of the math, but this is all very tractable math for freshmen and sophomores in school. That you have this wavelength that's related to its momentum. You have a kinetic energy that's equal to the energy of that you've imparted onto the electron through some accelerating potential, and it will and using those equations you can get an expression for the wavelength. At the speeds we're talking about, you do have to do a relativistic correction, so there's a little bit more math in there, but even if you use this uncorrected form, it'll get you kind of close. So here's a plot of the relativistic and non-relativistic wavelengths. For the tools that I work on, we're usually in the 100 keV to 200 keV range, and if we look at the wavelengths, they're really small. Again, as I said earlier, we're talking fractions of an angstrom. So the next step after that would be to build an electron microscope, which was done shortly after these early experiments with electron diffraction. They would also win a Nobel Prize in 1986, Ruska and Knoll, for building, I guess just Ruska, for building the first electron microscope. You can notice from the tool I showed you at the start of this talk, it's gotten a lot more complex than the instrument shown here. Right, so if we go back to that plot of resolution over time, the electron microscope opened up doors to seeing the nano world. After that, the microscope, up until the year 2000, rapidly progressed. I'm drawing a dashed line here around the 1 angstrom mark because we started to hit a limit, and that limit was our resolution was much larger. The limit that we hit was much larger than the wavelengths that I was just talking to you about earlier. But still, even with this resolution, we can see atoms. So Crew in 1970, this is a famous image. He looked at heavy atoms on carbon support. So these little white dots you're seeing along here are heavy atoms, and they're scattering so strong that you don't even see the thin carbon support that it's sitting on. And in the 90s, the discovery of nanotubes, this whole new area of materials research opened up with these electron microscope images of nanotubes and multi-walled nanotubes. So that was in the 90s, and that would give them the Kavli Prize in nanoscience for their work on nanotubes. But again, this resolution should be higher. We can do a lot with the resolution, but why are we hitting this barrier at a couple angstroms? Why can't we get below an angstrom? And the reason is because we have terrible lenses in our electron microscopes. And the analogy I want to make is with the Hubble Telescope. Maybe some of the optics people here are more familiar than I, but there was a spherical aberration on the Hubble Telescope that greatly degraded the performance, its performance. So they had to go back, and some clever people retrofitted it with a CS corrector that, once installed, the resolution really popped, and we could see distant galaxies and stars within the galaxies. So the before picture, this really lousy picture of the M100 galaxy, is more like what we're dealing with Another way to say it is our electron lenses are like a wine glass, has the quality of a wine glass. It's so you can see in the center of the wine glass we have a magnification of the background image, but at the edges it gets really blurred. So this is a spherical aberration effect, and it's what we have to live with in electron microscopy. That is the spherical aberration. So here's just a picture of the spherical aberration from in terms of a ray diagram, and it's just that rays far from the optical axis, so the rays A, for example, focus more strongly than those close to the optical axis, like rays C. We also have another aberration. There's many aberrations we deal with, but another major one is chromatic aberration, where different wavelengths are focused differently. So here, different wavelengths will be slightly different energies of electrons. But it's this spherical aberration that's really killing us. And that's the big breakthrough of the last 10 years in my field, that we have learned to correct the spherical aberration to break this 1 Angstrom barrier. Let's see, I don't know what's coming. Right, so the plot on the left is showing resolution of microscopes over time, the light microscope hitting its limit but set by the wavelength, and then the electron microscope, just technological progression up until the point that we start to hit the spherical aberrations in the lenses. And now the new microscopes are breaking this 1 Angstrom barrier by building a complex set of multipole lenses that work with computers to try and estimate and correct the aberrations. But at the end of the day, what we get is a tiny probe. So on the right, I'm showing you what the electron beam from a scanning transmission electron microscope, which I'll explain in more detail soon, but basically how small we can focus that beam tells us how good of our resolution is. So the image on the left is a slice through the electron beam in an uncorrected system, and the image on the right one, the tiny one, is a slice through the electron beam of an aberration-corrected instrument. So the lateral dimensions, that is the dimensions from left to right, so it's giving us our lateral resolution. The confinement up and down is what describes our depth of field. So if you've ever used a camera with a large aperture and you notice that your friend your friend up close is in focus, but your friend far away is out of focus, that's this depth of field effect. But what we're really concerned about is this lateral resolution. And with aberration correction, we're doing really well. We're below an angstrom. So we can now see things across all scales. So these are lead selenide quantum dots that are arranged in a very ordered way. So these aren't atoms, right? These are nanoparticles, and they're ordered in a way that allows you to tune the optoelectronic properties. With aberration correction, we can look at the long-range order of these particles, but we can also zoom in and see the atoms and the connectivity between these particles. So in this image that I'm showing, those dots are the atoms, and the larger dots are the nanoparticles. And when we've been studying this system, we found that there's actually strain and deformation at the necks that join these atoms, and they impact the electronic properties that we're after. So the point is here with aberration correction, it's easy to see easy to see atoms, and that's really really cool. I get really excited every time I see the atomic structure of materials. The tools that I've used throughout my PhD have been the neon stem on the left and an uncorrected F20, FEI F20. They're made by different companies, but the one on the left is the aberration corrected one, and the stacks you're seeing in between are the lenses in the microscope. Right. So how does this work? So there's a lot of different kinds of electron microscopes that work similarly and in different ways, but I want to explain to you the one that I use the most, which is the scanning transmission electron microscope. It's the one that focuses that electron beam to a tight point. So 100 keV electron beam comes flying off of typically a field emission gun and is focused to a point onto the surface of the sample. That beam is again, really tightly focused, fast-moving beam, and it crashes into our atoms, and we scan it across our sample, and we collect the atoms that are scattered. So if your electron beam is sitting on an atom, it's probably going to scatter really strongly into this annular detector here. And when it's off an atom, it scatters less so. And so this is how you build up your image. On the right is an image of another nanoparticle, and the atoms you see are bright because when this electron beam is positioned on those atoms, it scatters strongly into this detector. And the heavier the atom, the more strongly they scatter. So we can actually distinguish the amount of protons in the structure as well. So here I believe it's the slightly brighter atoms are cadmium, which I think has a periodic number of 48, and the selenium is periodic number of 34. So these little bright, the slightly brighter ones are the cadmium atoms in this nanoparticle. We can look at 2D materials. So now the game is what kind of questions can we answer? What kind of materials can we look at? We can look at 2D materials. That's been very exciting recently. Graphene is a 2D material of carbon atoms. So if you took graphite, like that maybe you find in a pencil, if they're still made of simple graphite, and you peeled off a single layer, you would get graphene. And you can actually do that. It's incredible. You can actually peel off a single layer of carbon atoms from graphite. And you can image it with these tools. So this is a picture of graphene, and we can identify grain boundaries in the graphene, so where the order changes. We can look at similar 2D materials. I'm getting a little feedback now. I don't know if you can turn it down. But. Right, so there's other 2D materials you can look at, like boron nitride. It's similar to graphene, except for instead of carbon atoms, you have alternating boron nitride. And you can also look at, you can find oxygen defects in the boron nitride. You can look at 2D silica, so it's like glass, but a 2D layer of glass. And at the top, we see an ordered 2D silica structure. And at the bottom, we found an disordered 2D silica, more like in a glass state that you would expect. I was personally interested in seeing how stacking of what the structure is of stacked graphene. So imagine 2 layers of graphene laid right on top of each other. It turns out if you lay 2 layers of graphene, or when you grow 2 layers of graphene, it often ends up in this configuration where half the atoms in projection lie on top of each other. But there's 2 forms you could have. You could have an AB stacking or a BA stacking. And this notation is just the difference between this one atomic bond length shift between the 2. If you look at bilayer graphene, so 2 layers of carbon atoms, you'll find that there are different stacking domains. So the image on the left is a sheet of bilayer graphene. The image on the right is the same bilayer graphene. We've just done some imaging tricks using the electron microscope to distinguish the 2 stacking orders. And with aberration-corrected tools, we can go in and we can see what's happening at the interface of these 2 stacking. So where the AB and the BA join, we can investigate what happens there at the atomic scale. So we've done this, and the images you see here are the atoms at these joined boundaries. There's 2 examples of it. So the one on top is a shear boundary. So the atoms AB, again, we're going from this AB shown here to the BA here. and we transition across the boundary using a shear, so shifting and vertically. We show B and C as a simulation of what the shear boundary looks like. C is just a toy model of what it looks like, and A is the actual structure in a real material. The other way you could do it is a tensile boundary. So this A-B transition happens by pulling the atoms perpendicular to the boundary. And again, we have a toy model, we have simulation, and we have the actual measured structure. When the atoms are close together, it turns out that they're brighter. And so we can use that to also measure what the width of this boundary is. You might notice that it looks a little dimmer at the boundary. So we can characterize the width of this atomic interface. And we can look at bulk crystals. So this is silicon, maybe the most famous crystal because it's used in so many electronic devices. And this was an image I took of silicon down the 110 direction. So this isn't a 2D material. This is a three-dimensional crystal, but we're looking down a high symmetry zone. All of the images I've shown you actually have been down high symmetry zones. So most things aren't 2D materials. Most things are these 3D crystals. So here's the silicon structure. Again, we have a periodic array of atoms, and I'm just rotating it, looking down different directions. And on the right, I'm showing you what the different high symmetry zones look like. So the 100 zone has this square looking lattice. The 111 has a hexagonal looking lattice. The 110 it's like they call it a dumbbell structure where you have these pairs. So if I go back, that's the dumbbell structure, right? They look like a bunch of little dumbbells. So most materials, most crystals are three-dimensional crystals. The nanoparticles that I've been showing you earlier, these are 3D crystals. When I say that you're seeing the atoms, you're actually seeing all the atoms in projection of that atomic column. So we're getting projection images of our specimen, and if the nanoparticle on the left and the nanoparticle on the right are the same structure. They're different particles, but they're the same structure. They're just oriented differently. And so in projection, we see different patterns. We can do more than just looking at the structure. We can pull out chemical information, and we can pull out bonding information from our atoms by collecting the spectroscopic signals that are emitted. So when this electron beam comes crashing down, it'll interact with the electrons inside the atoms and promote them to high energy states. And when it does that, our electrons lose energy, and we can collect the electron energy losses and sort them by the energy that they lost in what's called EELS, electron energy loss spectroscopy. We also get light that's emitted and X-rays that are emitted from the sample. And we collect them, we get these huge data cubes. But if you process it, you can turn it into chemical maps. So this is a crystal, 3D crystal structure, and with atomic resolution, we can see the lanthanum sites, the titanium sites, manganese sites. It used to be that this was something you could only do over a tiny little square at best, but the aberration-corrected tools also give us beam currents that allow us to take huge data sets. So it actually becomes a big data problem. This data set was collected by Julia Mundy, and it's absolutely gorgeous, so much so that it made the front cover of Nature Materials. But it was taken on our Neon, and if things are stable, you can probe the chemical structure with atomic resolution. There's also valence changes and fine details that can tell you stuff about bonding changes as well. But I will not get too much into that because what I'd like to talk about is tomography. So we have these projection images, right, of these crystals. And we want to try and understand what the material is from a single projection image, but this can be difficult. So this famous cartoon, or at least it's famous within the electron microscopy community, is a picture from the New Yorker, and it shows a projection image which you would assume to be a hand, but the actual structure might be a rabbit in a weird pose. So how do you know whether you're looking at a hand or whether you're looking at the rabbit? One way is to take a bunch of projection images, like shown at the top, from a bunch of different angles. So you're rotating your sample, and then from all these projection images at different angles, project them back and try and reconstruct the three-dimensional object. So this is the tomography process. All the electron microscopy requires sample preparation. So the tweezers are just showing you what a tiny little sample looks like. You can't even see the region that we're looking at, but it would be that little black thing at the tip of that. And you put it in a holder, and this holder goes in front of the electron beam, and it rotates. This is a hyperbranch cobalt phosphide nanoparticle, and you're seeing it rotating in the electron beam as we're collecting the images. And from those projection images, we can reconstruct the three-dimensional object, and we can slice into that object. So the top is what's called just an SEM image. So it's a little different from the projection images I showed earlier. It just shows you the surface topology. But with tomography, we get the entire 3D structure, and we can slice into it. So the bottom images are showing progressive slices. And we could identify these high-density cores in the particle that told us something about how they were formed. We've also found a lot of application for tomography in nanocatalyst aging in fuel cells. So these fuel cells load their catalysts onto a three-dimensional carbon support, and throughout the lifetime of the fuel cell, the performance degrades. And we correlated that degradation of performance to degradation of the particles on the surface of these carbon supports. So we did tomography throughout the cycling process, and we found coalescence of particles. So the before is the yellow and the red is the after, and you can find instances like these clusters where the particles join together, and we lose that surface area that we were talking about earlier, that we want to maximize the ratio of surface area to volume. And if particles come together and become bigger particles, you lose some of that catalytic activity. People have pushed the limits of tomography. Mary Scott, she's now at Berkeley. She was part of a team that reconstructed a gold nanoparticle down to 2.5 angstroms, so well below a nanometer. They've since gone even farther than that. So what you can see here is the lattice fringes in 3 dimensions from the atomic structure. I was interested in doing high-resolution work on nanoparticles for these catalyst applications, and found that when I tried to use aberration-corrected tools, I had this depth of focus problem. So when particles on the left in one region were in focus, particles on the right were out of focus. And this is the punishment of using a high-resolution aberration-corrected tool. You get the lateral resolution, but you lose the depth of field. So the system we were trying to look at was these copper-3 platinum nanocatalysts. They were treated with acid to give them a pore structure and improve their catalytic behavior. And we wanted to see the distribution of the pore structure of the particles and how these particles were placed on the carbon support. And we needed the resolution to resolve the internal pores of all these particles. So we needed sub-nanometer resolution over a large field of view. The problem is, if here is a tilt series, so here is me rotating this particle in the electron beam, and you see the particles moving around. What you might also notice, I'll play it again, is as the particles are rotating, some are coming in and out of focus. So this particle, for example, is out of focus, and then it comes into focus, and then it goes back out of focus. So if you want to try and do tomography, you can't have this. You can't have some particles in focus, some particles out of focus, and expect to reconstruct the three-dimensional structure. So what we did is we did a through focal series. So here I am changing the focus through the entire specimen. Some people call this depth sectioning. And then I tilted the sample and did a through focal series on that. And then I tilted the sample again, did a through focal series on that. and did that for all the tilts. So it's a normal tomography plus step sectioning. And the end result was high resolution reconstruction of all the nanoparticles across the support over a very large field of view. So yeah, this is the same data set you saw on the title slide. It's just a fancier animation of it. Right, so again, it's important to remember that we get the entire structure, we get the internal structure, we can slice through these particles, and we can characterize the surface area to volume ratio. And you can tell from these porous particles there's a lot of surface area. We also found little tiny particles that had no pores inside them. Yeah, so I guess the last thing I just want to plug at the end is my promotion of open science and open source software. So open science is the idea that work should be transparent, transferable, repeatable. If it's software, it should be cross-platform, open source, and extendable, so other people can use it. They can take it and then add to it. We've had I've worked a lot on developing 2 open source projects. So one is the Cornell Spectrum Imager. So all that spectroscopic data sets that I was talking about earlier, all the details of that are built in this open source platform. But what I'm really actively working on now, in addition to all of the science, so this is just a tool to aid me in my research, is the Tomebase, which is a tomographic tool set. Here's some visualizations that were made by Elliot, another lab mate of mine, using the Tomebase package that we're developing. And it's more nanocatalysts with different loading weights. And the blue ones are the internal particles, and the red ones are the particles sitting on the outside of the carbon. And this can all be visualized. Like you can go make the same visualizations with these data sets using Tomebase. There's a 3-minute video that shows this. Again, this is a tool you can start playing with any volumetric data set. So a stack of images, or a stack of images you take on your iPhone, or with your light microscope you could load into it, or a simulation that has 3-dimensional volumetric data. It comes with some sample data sets that you can use, but this is just another catalyst data set. You can do right, so all the standard stuff with speed this up. I think this was not the same video that I intended to show. But yeah, you can do volumetric rendering, you can do surface rendering, you can slice it, you can do Fourier transform analysis. I apologize, this wasn't the complete video. But it's open source. If you go to tomeviz.org, we're building more tutorials for that. You can look at the source code. You could write code for it. You can. It has Python libraries, so you can do your data processing within Python. And I think with that, I will conclude. It'll leave room for questions. I can also talk a bit about my experience as a physicist and where I'm at today and where I plan to go. But I need to acknowledge the plethora of people that I've worked with over the years. There are many people, and I couldn't have been involved with the projects I've been involved with without them. So I'll hand it over to you, Will. Do you?
Okay. Can you hear me?
Yeah, I can hear you.
Okay, so let's thank our speakers. Fantastic. Okay, so I want to make sure that we open it up to questions. If you're listening on the live stream at Google+, please use the Q&A feature there with the Google+ Hangout. We can see your questions and answer them that way. If you are on Twitter and following along on YouTube, please use the hashtag GHO seminar, and we'll be watching to see if we have anything pop up there. Do we have any questions here locally? UCA folks, you guys got any questions for Dr. Hovden? Lucas, fire away.
Real quick, I've had some experience with atomic force microscopy rather than electron scanning or scanning microscopy. And so you say that you can see through the atom, whereas the way that atomic force microscopy can't. And so just to make sure that I have an understanding, it's because how do you actually get inside the atom with the electron microscope? Is it just because of the fact that you can tell the loss of energy, or is it the scattering?
Right. I'm glad you brought up. There's a whole other field of microscopy that I kind of jumped over, and that is the AFM community and the scanning tunneling microscopy community. The atomic force microscopy can do atomic resolution imaging fantastically. So the scanning tunneling microscopy can probe electronic states. These are all surface measurements. So the difference between our tools, what our tools are able to look at, and what AFM is able to look at is primarily, the primary difference is that we look at the entire structure in projection, and AFM and STM looks at the surface. There's also some subtle differences as to what kinds of materials work well for these two techniques, but that the primary difference is surface versus projection measurements.
Okay. So I guess for myself to get a little bit clearer, when we use the electron, we're using the electron's wave function, and then how that wave function gets scattered, or is it the electron itself? Are we still talking wave part of it, which we primarily focused on?
Right, right. Let me jump back to a slide I showed earlier. All right. Are we full screen right now?
Yes.
Right. So what I'm showing on the right side is actually the wave function squared. So it's the intensity.
Wow.
It's the square of the wave function.
Okay.
But it's across depth. So the vertical direction is each line is the wave function, and then you can imagine the next line is what the wave function looks like after it's propagated a little bit. So the entire thing is the electron propagating across 150 nanometers. So a 2D slice or a line, if you draw like one of these dashed lines, that would be, that profile plot would be what that wave function intensity looks like there. But of course the wave function is a complex wave, so how it interacts with the material, you do have to consider that the entire complex wave function. It becomes a multiple scattering problem that you can spend a lot of time thinking about the physics of. But in the simple picture, just imagine that this electron beam is a high intensity, highly focused beam, and where it's at a maxima, it will scatter most strongly off of an atom. So if an atom is in this deep red area, then you're going to get more signal. And if the atom is off to the side of it, then this wave function is not going to interact very strongly with that atom, and it won't scatter very strongly. Does that make sense?
Yes, yes, that's awesome. That is really remarkable.
Yeah, there's actually a whole discussion a whole nother area of research that I've gotten into during my PhD is channeling effects. Maybe I have a slide. Okay, here's a slide. This is a cool phenomena that happens. So you can see the full screen right now?
Yes.
Right, so these are the same profiles of the wave function of this focused electron beam. And the image on the new images that I'm showing is the same thing, At the top is the electron beam coming in and going out. If you place a column of atoms, so this is a simulation, but if you place a column of atoms, say silicon atoms, in front of this electron beam, the electron beam doesn't just scatter off of the atoms. Part of the electron beam will get sucked onto the positive column, and it'll propagate down that positively charged column. And we have this really nice molecular orbital model that describes this behavior. You can read about it in the PRB we published in 2012. And what's weirder is if I place a second column, so now I have a single column of atoms where this electron beam has been pulled onto and it propagates down. If I place the next one adjacent to it, the electron beam that's sucked onto the column will now jump back and forth.
Oh my God.
So it's actually can be described by a bonding, anti-bonding molecular orbital picture of the 2D eigenstates of these atomic columns. So the electron wave function is basically beating back and forth between the two columns. And
wow. That is just really nice physics there. Really beautiful to see the quantum mechanics, basically, right? It's just any students that are currently in senior level quantum, it's like, yes, I understand that. Seen that before. Cool. Do we have any questions from our audience there at Suffolk University?
I don't think so. A lot of our audience left because they have a midterm tomorrow morning. So.
Yeah.
I don't think so. Do you guys have questions?
No.
No?
Okay. So, well, Robert, I've got a question for you.
Sure.
You've got some really cool hardware there, and it looks like you guys are doing some really amazing physics. Do you have any REU programs or any sort of stuff where students can come work in your lab or work there at Cornell?
So again, I am a postdoc, but Cornell has a great REU program. Let me plug it. Right, so the Cornell Center for Materials Research has an interdisciplinary REU program. So you could be in a wide range of, I guess, departments, but we're all working on similar things in materials, trying to solve problems in condensed matter physics, materials, chemistry. There's a lot of overlap between departments here. So if you go to the ccmr.cornell.edu/REU website, you can get information on that. And they take people, my understanding is people from a wide range of disciplines and backgrounds are admitted into the program.
Cool.
I was looking at the 2015, so last year's dates had an early acceptance application that started in December. So the earliest you could apply is probably this year will probably be around that December timeline.
Well, we'll definitely be paying attention and watching for when that due date comes out because we want to get some students up there. It's really cool.
Yeah, it's a fantastic place. Let me see. I think yeah. So this is an overview of Ithaca Cornell Campus, and it's beautiful. It's a great town. Highly recommend people to apply to the REU. It's a good experience. I recommend REUs in general to anyone that wants to go to grad school. That's my biggest piece of advice: is do something in a lab, get some work. It will help a lot.
Yeah, it's always good to see something different from what you're used to. And going to another institution, especially from a small school that's primarily undergraduate to an R1, that's an eye-opening experience. So getting to see real hardware and some postdocs and grad students that are working on projects, that's awesome. That is awesome. So what was your career trajectory? How did you get interested in material science? How was it electron microscopy was the thing that just fuels your passion?
Yeah. So here I made a little slide. I had to reflect on the history of my life for this talk. Right. So your question, how I became a physicist, and I'll call myself an atomic photographer. That's my elevator pitch to non-science people.
That's a good one.
I started as an undergrad at the Georgia Institute of Technology, Georgia Tech, and I was a physics major, but I minored in material science. So I already had an eye for nanoscience, but was really sold on the coursework of the physics major. I was really interested in everything. I wanted to join every research lab. I was not necessarily sold on material science or physics. I liked physics coursework. I did summer research at Jet Propulsion Labs, so I was applying to lots of REUs and applying to various places that would take a summer researcher, and Jet Propulsion Labs said they would take me, so I did some summers there as a software evolutionary computation guy. So not a physicist, but solving cool problems using new algorithms. And then I also joined at my senior year an AFM, so it was great, it was brought up, doing atomic force microscopy of graphene at Georgia Tech. And I was working, part-time, so 10 hours a week in that lab. And then I wanted to do a PhD program in materials. And to be honest, it didn't have to be physics, but I liked physics departments, but I was also applying to materials programs. And that's another thing to keep in mind. If you're a physicist, you're prepared to solve a lot of problems in a lot of different fields. So don't necessarily pigeonhole yourself to just physics. There's cool problems everywhere. And I was already into characterization of materials a little bit, and when I saw the electron microscopes and the work that what would become my advisor, David Muller, was doing, I got really excited about it. And so I dove into electron microscopy and characterization. And I've been doing the physics of characterization and of materials since. And now I'm a postdoc in Professor Kirkudis' lab, doing similar things, but with low temperature. So we're now going to liquid nitrogen and maybe beyond that to understand phase transformations in materials. So my trajectory is somewhat predictable, but there was certainly a phase where I was just trying to search what I wanted to do, and that was as an undergrad. So where your students are at. And I don't know if I have an answer. I still talk to an economist and I get excited about their work. Science is fun. I don't know. I don't draw as many distinctions between disciplines.
So what's your next step with the postdoc? When does that wrap up? What's your next plan? Are you going to do a startup with this Tomebase company? Or what's your trajectory beyond this?
Right. So open source software is a viable business model, but it's a tough one. No, Tomebase is just so I can have an open source tool that serves my field of research. My goal is to be an educator.
Cool.
Be at a university.
Fantastic. I think coming from...
Say again? I think I lost you.
Sort of what being an educator at an undergrad only or a master's or R1 type institution, they're all different. And so you get more experience with, okay, there are pros and cons to each institution. So...
Absolutely. Yeah, so I'm looking more at R1. I want to run a lab,
yeah.
which occupies a lot of your time.
Yes.
So
grant writing particularly.
Yeah.
Well, you mentioned definitely applying for REUs. Do you have any other advice for current undergrads? If you could talk to yourself you know, back when you were an undergraduate student, what message would you send into the past that you might share with these students that would have benefited you?
Yeah, I would echo what I was saying earlier, that just find interesting problems to solve and work with people that will have you on their team. You can solve, especially if you're a physicist, you can solve a lot of interesting problems. So just find those advisors that can help you through them.
Mm-hmm. Yeah.
And that's really advice to those that want to go to grad school, which is the path I'm familiar with. The career path, I've been a student my whole life.
Yeah, I find myself with the same problem, is that I know how to advise you to go into grad school, but finding a job in an industry is not what I know how to do. So I'd like to learn that.
Right.
But you've given a fantastic seminar. Definitely great level for undergraduates to understand what you're doing, and then to tease the students and myself indeed to say, wow, this is really awesome physics that you guys are doing. Want to make sure that we don't have any other questions. Do we have any other questions here at Tomebase? No, let me check. We'll check Twitter just to be sure. You guys there at Suffolk have anything come up while you were watching or listening?
We're good.
Yeah. Good? Okay. All right. Well, Robert, this is fantastic. I really appreciate your time. You'll be getting an email from me to kind of wrap up what our business is with the Hangout, but this has been fantastic. You've given a great seminar. Definitely have learned a lot from this, and I think our students appreciate it. Let's give Robert another round of applause. Okay, well, thank you very much. This is the end of the seminar. I'll stop the broadcast, and then we can wrap up with our guests here momentarily.